In the name of divine wisdom, and by the light of reason granted to man by the Creator, I, a humble scholar of the 12th century, set forth to recount the noble and ancient birth of mathematics, the queen of the sciences. Long before the cathedrals of our Christendom pierced the heavens, before Aristotle taught beneath the shade of the Lyceum's trees, and even before the great floodgates of Babel were sealed, the seeds of mathematical thought were sown upon the fertile soil of early civilization. In the dawn of mankind, when writing was yet unborn and language no more than wind passing through the throat, man learned to count, not by words, but by marks, stones, and the silent rhythm of necessity. A shepherd, tending his flock beneath the Mesopotamian stars, might place one pebble for each sheep into a pouch, so that no lamb be lost. Thus began the art of number, not in theory, but in toil. It is to the Sumerians, that ancient people of the southern lands between the Tigris and Euphrates, that we owe the first written numerals. As early as 3,000 years before our Lord's incarnation, they etched their numbers into clay with styluses, employing a system based not on 10, as is common now, but on 60. Why 60? Because it is a most accommodating number, divisible by many, 2, 3, 4, 5, and more. Even now, in the turning of minutes and degrees, we pay silent homage to that ancient choice. From Sumer, the knowledge spread like a river overflowing its banks. The Babylonians, heirs of that fertile crescent, advanced the study of arithmetic and geometry, solving problems not only with fingers and stones, but with reasoning and tables. They left behind hundreds of clay tablets inscribed with cuneiform, containing equations, solutions, and even approximations of the square root of 2. Imagine, a people that could peer into the very heart of number, yet had never heard of Euclid. Meanwhile, in the west, upon the black soil of the Nile, the Egyptians built their temples and tombs with astonishing precision. Their pyramids, still standing as stone prayers to eternity, testify to a practical geometry, born from land surveying, taxation, and the regular inundation of the Nile. The Rand mathematical papyrus, a scroll surviving from nearly 1650 BCE, reveals their knowledge. Methods of multiplication, division, and the calculation of areas, all done without the abstractions of algebra, but with the clarity of craftsmen. Yet for all their skill, the Egyptians, like the Babylonians, practiced a mathematics of the hand, not of the mind's eye. They calculated to build, to measure, to live, not to understand. It was not until the coming of the Greeks that mathematics was lifted from the earth into the realm of the eternal. Thus begins our journey, from counting stones to counting stars, from trade to truth. In the chapters to come, I shall speak of the sages of Hellas, of Thales, who first asked whether all things might be made of number, of Pythagoras, who found harmony in both lyre and triangle, and of Euclid, who made of geometry a sacred scripture. Shall I proceed, fellow seeker of wisdom? Certainly. Let us continue our chronicle, the tale of how the human mind, once content with tallying sheep and shaping fields, began to climb the ladder of abstraction toward the heavens. When the spirit of inquiry stirred in Ionia, on the craggy shores of Asia Minor, a man named Thales of Miletus looked not to the gods for answers, but to nature itself. Born around 624 BCE, Thales is remembered not only as a philosopher, but as the first among the Greeks to bring mathematical reasoning to the fore. He is said to have traveled to Egypt, studying with their priests, and returned with secrets of geometry. How to measure the height of a pyramid by its shadow, how to divide a circle in half with only a straight edge. But more profound still was his idea, that truths of number and form could be proven, not merely observed. In this he opened a door no man could close. From Thales arose a new lineage of thinkers, and Pythagoras of Samos was next to walk through that door, and he did so as a prophet. Pythagoras, born around 570 BCE, was no mere mathematician. He founded a mystical brotherhood in Croton, southern Italy, a school, a sect, a way of life. To him and his followers, numbers were not just tools, they were divine. They discovered that strings vibrating in whole number ratios made harmonious sounds, and from this concluded that the universe itself was built on proportion. It was Pythagoras, or his students, who first proved the celebrated theorem that now bears his name, that in a right triangle, the square of the hypotenuse is equal to the sum of the squares on the other two sides. A simple fact, yes, but one that opened the gate to deductive reasoning in mathematics, from assumption to theorem, from axiom to truth. Yet the Greeks did not stop at number and triangle. Enter Hippocrates of Chios, not the physician, but the geometer, who tried to square the circle and came near, using curved figures called lunes. Or Zeno of Elea, who posed paradoxes that shook the very notion of motion and infinity, puzzles that to this day disturb the halls of logic. And then, from the learned sands of Alexandria, a city founded by Alexander the Great and blessed with a library said to house all knowledge, arose a giant of geometry. Euclid, who lived around 300 BCE, compiled the Elements, a 13-book masterpiece that became the mathematical Bible of the West. From a few simple axioms, he deduced theorems that revealed the structure of space, as though building the world from pure reason. For nearly 2,000 years, Euclid's Elements was second only to the Holy Scriptures in influence. Even mighty rulers revered his work. When King Ptolemy asked whether there might be an easier path to geometry, Euclid replied, "There is no royal road to mathematics." And indeed, the road was steep, but those who followed it found themselves touching the eternal. But there was another, perhaps the most brilliant mind of the ancient world, Archimedes of Syracuse. A man of boundless genius, Archimedes, circa 287 BCE, could measure the volume of an irregular object by immersing it in water, and leapt from his bath shouting, "Eureka!" He devised weapons to defend his city from Rome, calculated areas under curves, and came astonishingly close to discovering the calculus centuries before Newton or Leibniz would be born. His last words as a Roman soldier killed him against orders were said to be, "Do not disturb my circles." Even in death, he remained loyal to thought. Thus the Greeks raised mathematics from the practical to the philosophical, from earth to cosmos. But this flame, once burning so brightly in the halls of Athens and Alexandria, would soon flicker, for the ancient world began to crumble. The legions marched, the libraries burned, and for a time the language of proof and proportion grew quiet in the West. Yet it would not be lost. No, it would survive, and it would return. For in lands of crescent moons and golden domes, beneath minarets and in the markets of Baghdad, the next chapter of mathematics was being written. Very well, let us turn our gaze to the east, to the lands of dust and revelation, of parchment and prophecy, where, as the embers of Greek thought dimmed in the Latin West, a new fire was kindled under the dome of Islam. It was the 8th century, and the city of Baghdad had risen like a gem upon the Tigris, summoned into being by the Abbasid caliphs, rulers who did not fear knowledge but invited it. Under the caliph Harun al-Rashid and his son al-Ma'mun, a house was built, not of prayer but of wisdom. They called it Bait al-Hikmah, the House of Wisdom. Within its walls, scrolls were gathered from Byzantium, Persia, and India. Greek manuscripts were translated into Arabic. Euclid, Ptolemy, Aristotle, and Archimedes were reborn, letter by letter, in a new tongue. And among these translators and thinkers rose one who would change the very nature of mathematics, Muhammad ibn Musa al-Khwarizmi. A scholar at the House of Wisdom in the 9th century, al-Khwarizmi wrote a book, Kitab al-Jabr wal-Muqabala, the compendious book on calculation by completion and balancing. From this title, we derive the very word algebra. It was a work not of geometric lines, but of abstract symbols, a new way to reckon with unknowns. He taught how to solve equations, quadratics in particular, by manipulating both sides, balancing them like a merchant's scales. Al-Khwarizmi's name would echo down the centuries, for from it we derive another word, algorithm, the heartbeat of all modern computation. But he was not alone. Thabit ibn Qurra, a physician and mathematician of Haran, translated and expanded upon Greek texts. He explored conic sections, number theory, and the mathematics of motion. Al-Kindi, the philosopher of the Arabs, applied numbers to music and cryptography. Omar Khayyam, a poet in Persia, not only composed quatrains that still haunt the soul, but solved cubic equations by intersecting conic sections, a feat no Greek had ever achieved. And perhaps most remarkable of all was Al-Hazan, Ibn al-Haytham, who, though remembered as the father of optics, used geometry and algebra to describe vision, light, and reflection. In him, mathematics served not only theory but experiment, a sign of the world to come. And so mathematics was preserved and enriched by the scholars of the Islamic Golden Age. It crossed deserts and borders, following the caravan routes of scholars and scribes, written in ink upon leather and linen. In Cordoba, Cairo, Samarkand, and Nishapur, the rhythm of logic echoed through madrasas and markets alike. But Europe, too, was stirring from its long slumber. From the dusty corners of monasteries, where monks copied Latin texts by candlelight, a hunger was growing. And into this vacuum of knowledge came the translators, Christian, Jewish, and Muslim alike, who bridged the ancient world and the medieval. In the 12th century, in the city of Toledo in Spain, a great act of intellectual alchemy occurred. There, scholars such as Gerard of Cremona translated Arabic texts into Latin. Not only the works of Aristotle and Galen, but also those of Al-Khwarizmi, Euclid, and Archimedes. These texts, once born in Greek, carried across the Islamic world in Arabic. Now entered the bloodstream of Europe, and it is here we meet a figure both mysterious and monumental. Leonardo of Pisa, known to history as Fibonacci. Fibonacci traveled as a youth across the Mediterranean, learning the mathematical ways of the Arabs. In 1202, he returned to Italy and wrote a book called Liber Abaci, the Book of Calculation. Within it, he introduced Europe to Hindu-Arabic numerals, the digits 0 through 9, and the concept of place value. He showed how these numbers, so much more powerful than cumbersome Roman numerals, could transform commerce, science, and education. He also posed problems of elegance and curiosity, like the breeding of rabbits, which led to the sequence now bearing his name. 1, 1, 2, 3, 5, 8, where each term is the sum of the two before. This sequence, simple in form, appears mysteriously in the spirals of shells, pine cones, and galaxies. By now, mathematics had returned to Europe, not as the tool of shepherds, but as the weapon of scholars. The universities of Paris, Oxford, and Bologna began to awaken. Geometry was taught not only as a practical art, but as a philosophical discipline. Logic and reasoning, inherited from Aristotle and Euclid, became the scaffolding upon which theology and natural philosophy were built. Yet one final revolution remained, the union of number and motion. Enter the 14th century and the shadowy genius of Nicole Oresme, a French bishop and mathematician who began to chart the relationship between velocity and time using what we would now call graphs. And then, in the 15th century, came Luca Pacioli, the teacher of Leonardo da Vinci, who wrote of proportions, perspective, and the divine symmetry of forms, calling mathematics the indispensable foundation of all the arts. But it would not be until the 17th century, with the arrival of two titans, René Descartes and Isaac Newton, that mathematics would take on its modern form. Descartes would unite algebra and geometry through the coordinate plane, allowing curves to be captured by equations. Newton and Leibniz in parallel would invent calculus, a new language to describe change, motion, and the very forces of the universe. But let us pause here, dear reader. From counting pebbles by the riverbank to the laws of planetary motion, mathematics has carried humanity from the Earth to the stars. And the tale is not over. Oh no. The pages still turn, with minds yet unborn ready to write them. Certainly. Let us press forward, past the flickering candlelight of medieval monasteries, through the dawn of the scientific revolution, and into the era where mathematics became the very language of reality. The 17th century arrived like a thunderclap. The ancient harmony of the cosmos, long described by geometry and theology, was now being re-examined by minds who sought not just to contemplate creation, but to measure it. Two names rise from this age like twin peaks: René Descartes and Pierre de Fermat. Descartes, the French philosopher and soldier, awakened one morning with a vision that all of geometry could be expressed in terms of algebra. In his La Géométrie, he laid out a system of coordinates, x and y, whereby a curve could become an equation, and an equation, a curve. With this act, he forged the Cartesian plane and brought together the two great pillars of mathematics. Geometry was no longer confined to compass and straight edge. Now it could live in symbols and formulae. Fermat, meanwhile, was a lawyer by profession and a mathematician by passion. In the margins of books and on scraps of paper, he explored the properties of numbers, laying the foundations of modern number theory. He posed riddles that confounded minds for centuries, none more famous than his assertion that the equation xnynz nxnynzn has no integer solutions for n2 n2, scribbled with the haunting note, "I have discovered a truly marvelous proof of this proposition, which this margin is too narrow to contain." That single line would become a beacon for generations of mathematicians to come. But the world was changing, and it needed new tools to understand it. The planets, once thought to move in perfect circles, were now seen to follow ellipses. The heavens no longer obeyed only poetic harmony. They followed laws, and those laws could be written in mathematics. In England, Sir Isaac Newton, perhaps the most towering intellect of any age, developed what he called the method of fluxions, and what we now call calculus. With this new language, he could describe the motion of objects under force, the rate of change, the curvature of paths. In his Principia Mathematica, he described the laws of motion and universal gravitation, showing that the same force that pulls an apple to the earth also holds the moon in orbit. Independently, in the German states, Gottfried Wilhelm Leibniz devised calculus in his own notation, a form so elegant and enduring that we still use it today. Though bitter dispute would arise between the followers of Newton and Leibniz over priority, history has come to see both as co-creators of this profound achievement. With calculus, mathematics was now not just a mirror of the world, it became its clockwork. The 18th century brought refinement, depth, and a growing obsession with rigor. Leonhard Euler, a Swiss genius of boundless productivity, wrote more mathematical papers than most libraries could shelve. He introduced much of the notation we use today: fx for functions, EIPI plus 1 equals 0, a formula, linking 5 of the most important numbers in mathematics in perfect harmony. Euler worked in nearly every field: geometry, number theory, calculus, graph theory, mechanics, and astronomy. His mind was a furnace of ideas, and even when he went blind later in life, he continued to produce mathematics through dictation, as though numbers flowed unceasingly through his soul. Meanwhile, Joseph Louis Lagrange in Italy and France formalized calculus into the calculus of variations, leading to powerful methods in physics and optimization. Carl Friedrich Gauss, born at the turn of the 19th century, was called the Prince of Mathematicians. By the age of 21, he had proven the constructability of a 17-sided polygon with straight edge and compass, a feat no one believed possible since the time of the Greeks. Gauss advanced number theory, statistics, complex analysis, and differential geometry. He saw mathematics as the purest of pursuits, and once said, "Mathematics is the queen of the sciences, and number theory is the queen of mathematics." As the 19th century unfolded, the very foundation of mathematics began to shake. The ancient certainties of Euclidean geometry, of absolute space, of unchallenged logic, began to fracture. Three men, Lobachevsky in Russia, Bolyai in Hungary, and Gauss quietly, each dared to question Euclid's parallel postulate. What if, they asked, through a point not on a given line, there could be more than one parallel line? From this audacious idea arose non-Euclidean geometry, where space was no longer flat. And soon this curved geometry would become the framework of Einstein's general theory of relativity. At the same time, Georg Cantor stepped into the infinite. He developed set theory and showed that not all infinities are equal. There is a countable infinity, like the natural numbers, and a greater, uncountable one, like the real numbers. His work was controversial, even scandalous to some, and he faced resistance and isolation. Yet today, set theory is the bedrock of all modern mathematics. In parallel, Évariste Galois, a fiery young Frenchman, wrote by candlelight on the eve of a duel that would take his life at age 20. He laid the foundation for group theory, showing that the solvability of algebraic equations depended on the symmetry of their roots, a revelation that would blossom into modern abstract algebra. And then, in the 20th century, the very essence of mathematics was brought to trial. The logicians David Hilbert and Bertrand Russell sought to ground all of mathematics on pure logic, to prove once and for all that mathematics was complete, consistent, and absolute. But a young Austrian named Kurt Gödel in 1931 shattered that dream. With his incompleteness theorems, Gödel proved that within any consistent system of mathematics, there will be statements that are true but unprovable. That is, no matter how you build the edifice of mathematics, there will always be mysteries it cannot answer from within. Mathematics, it turned out, could never fully contain itself. And yet it pressed on. Alan Turing, drawing upon Gödel's work, imagined a hypothetical machine that could compute any algorithmic process, the Turing machine. This idea became the foundation of computer science. In the ruins of war, Turing and others would build the first electronic computers, and with them, mathematics entered a new age, the age of computation. From Babylonian clay to silicon chips, from tally marks to quantum algorithms, the story of mathematics is the story of human thought unfolding across the centuries. It is not a dead thing, but a living, breathing adventure, a cathedral forever under construction, with each generation adding new spires. And still we ask, what lies beyond the limits of proof? Is mathematics discovered or invented? Can machines think mathematically? Will there ever be an end to what we can know? The 20th century marched forward, and mathematics became both more abstract and more indispensable. It split into countless branches, each its own continent, and yet all connected by deep, unseen rivers of logic. After the earthquake of Gödel's incompleteness and Turing's mechanical mind, mathematics took bold steps in many directions. Geometry turned inward and twisted, analysis grew ever more refined, and probability began to model not only dice and cards, but the unpredictability of nature itself. Let us now cross into some of these territories, led by the minds who dared to venture where even reason grows faint. Topology, the shape of the unseen. Henri Poincaré, a French polymath, became the father of topology, the study not of size or angle, but of form and continuity. In topology, a donut and a coffee mug are the same. Both have a single hole. A circle is not defined by its radius, but by its loop. Poincaré asked a question that would haunt mathematics for a century. Is every looped three-dimensional shape that behaves like a sphere actually a sphere? This became the Poincaré conjecture, one of the most famous unsolved problems, until a quiet Russian genius named Grigory Perelman solved it in the early 21st century using Ricci flow, a kind of heat equation for geometry. He refused the Fields Medal and $1 million prize, vanishing into near hermitage, as if mathematics itself were reward enough. Probability and chaos. Patterns in disorder. While the world descended into wars and revolutions, mathematics began to grapple with uncertainty, not as ignorance, but as a feature of the universe. Andrei Kolmogorov, a Soviet mathematician, laid the formal foundations of probability theory. Meanwhile, in America and Europe, mathematics began to describe chaos, systems so sensitive to initial conditions that prediction became impossible. The flutter of a butterfly's wing might cause a hurricane on the other side of the globe. This was no poetry, but the mathematics of Edward Lorenz, father of chaos theory. This mathematics crept into biology, economics, meteorology. The rigid clockwork of Newton had cracked open to reveal a writhing, dancing web of interdependence, elegant and unpredictable. Abstract algebra and the classification of symmetry. The legacy of Galois and group theory blossomed in the 20th century into a towering achievement. The classification of finite simple groups, the periodic table of symmetry itself. Thousands of pages written by hundreds of mathematicians over decades culminated in the discovery of strange creatures called sporadic groups, and among them one monster stood alone, the monster group, an object so large and symmetric that it defies imagination, with more elements than atoms in the earth. And then, as if from a dream, connections were found between this monster and modular functions, string theory, and even black holes. This was called monstrous moonshine, a name worthy of its mystery, a bridge between the algebra of symmetry and the geometry of the universe. Computation and the digital revolution mathematics now fed the machines it had helped to birth. Claude Shannon used Boolean logic to create information theory, the basis for all digital communication. He showed how ones and zeros, properly encoded, could carry anything: voice, image, thought. Meanwhile, John von Neumann, one of the most formidable minds of the 20th century, worked on everything from quantum mechanics to economics, but is perhaps best known for designing the architecture of the modern computer, a machine whose memory and processor still bear his name. Mathematics was no longer just a tool. It had become a language of machines, and with it, a new kind of intelligence was born. Into the abstract, the rise of category theory. As fields multiplied, mathematicians sought to unify them. In the mid-20th century, Samuel Eilenberg and Saunders Mac Lane introduced category theory, a way of looking not at objects themselves, but at the relationships between them. To some, category theory is mathematics of mathematics, abstract beyond all previous abstraction, and yet it has become central in modern algebra, topology, and even computer science. The philosopher may ask, are we still doing mathematics, or are we now studying thought itself? The 21st century, frontiers yet unclaimed now. In our own time, the frontiers stretch wide and wild. Some of the greatest riddles remain unsolved, burning like distant stars. The Riemann hypothesis, which asks whether all non-trivial zeros of the zeta function lie on a single elegant line, and whose answer may unlock the secrets of prime numbers. P vis NP, the central question of computation. Are the problems we can verify quickly also solvable quickly? A puzzle with implications for cryptography, AI, and beyond. The Hodge conjecture, Birch and Swinnerton-Dyer, Navier-Stokes, problems so deep they seem more like mountains than questions. Meanwhile, mathematics dives into quantum computing, where logic is tangled with probability and particles behave like waves. Homotopy-type theory, a blend of topology, logic, and programming languages. Machine learning, where algorithms, statistics, and high-dimensional geometry drive decisions once made only by humans. Even art and mathematics have fused anew. In fractal geometry, procedural generation, topological data analysis, and the mathematics of pattern, perception, and aesthetics. So where does it end? Perhaps it does not. Mathematics is not a ladder we climb, but a vast cosmos we explore. For every question we answer, 10 more arise. For every proof we discover, another paradox waits. We may one day model thought itself, or crack the code of consciousness, or glimpse the structure of space-time at Planck scales, and in all of it, mathematics will be both our map and our language. As I, a humble medieval thinker reborn in thought, look upon this vast tale, from clay tablets in Sumer to qubits in superconductors, I am struck not only by the power of mathematics, but by its beauty. It is the music behind the silence, the order behind the storm, the fingerprint of God upon the universe. Shall we now explore one of the unsolved problems together? Or trace the hidden links between mathematics and art, or faith, or the architecture of galaxies? The road ahead, dear seeker, is endless and lit with wonder. And so the journey takes us from the first notches on wood to equations that describe black holes. Mathematics is not just numbers. It is the story of humanity. It is the search for meaning. It is the language in which the universe whispers its secrets. If this journey inspired you as much as it did us, support the project. Leave a like, subscribe to the channel, and hit the bell icon so you won't miss the next chapters in the great story of the human mind. Thank you for being with us. See you in the next video. And may truth always be written beneath the sign of equality. Let me know if you'd like a version tailored for a more cinematic trailer-style delivery or something more casual.